Yeah.
I was. It's not a question. I want us to. I want you to explain one more time the part. Can you scroll up? And yes, this part after we. Okay, after we did this. No. Down.
Uh-huh.
After we did this substitution or
Okay, yeah. This one, right? This
нет,
one.
ниже надо.
Yeah.
Так, вот, here. Okay, after I understand that this should be we should find the minimum value of this. Okay, this как это, length, and after this I got lost.
Okay. Well, okay. This is very simple, actually. The only thing I wanted to say is that is that look, this
no,
guy.
sorry.
Yeah.
And also I missed why we dropped why we dropped this
SX, right? SX. Okay, yeah. Because we don't we dropped SX here at this point because we are not really interested in the magnitude of X. Okay, so we assume, okay, this will come later, okay, but we assume that U of X, you know, this okay, so if you have, let's put it this way, okay, let me try to explain. So basically what we had UG, because it kind of correlates with the notion of signal subspace, and therefore I will explain UG transpose, yeah, UG transpose UX SX, and we want to minimize the Frobenius norm of this, okay? Maximize Frobenius norm of this, right? Okay, so look, if you access X is something that that comes from your data, right? Your data are decomposed US UX SX VX transposed, right? And this decomposition, what it takes, you have columns of U, right? So this is matrix UX, right? You have diagonal matrix of singular values S1. Let's call them sigma 1, sigma 2, sigma n, right? And then you have rows of your matrix Vx transpose. Okay, so right, so the spectrum of singular values will basically tell you the amount of energy, if you will, that is contributed to the approximation of your data. I'll explain, to the approximation of your data with the corresponding component. Because look, you say that it's sigma 1 times U1 transpose sigma V1 transpose. Okay, I removed the X here, right? So, but this is just the element, right? This is the first vector, this is U1, this is U2, this is U3, and etc. Right?
Yes, this
Yeah.
I understand this.
Okay, so and the amount, this is orthogonal, so it's unit norm. This is orthogonal, it's also unit norm. So it's just shape, okay? It's just a shape, all right? It's not the amplitude. The amplitude is contributed by this guy, all right? So then there is another one, U2 V2 transpose, another shape, okay? Another pattern, right? Another some, and then it's scaled. Okay, usually we draw a spectrum of singular values. We call it a spectrum, and it's normal mathematical title. It's a spectrum, and this is singular values. And you usually select, to form this matrix UX, you usually select several of them, not all. Okay, but you assume that all of them are powerful enough. Okay, we will see today, but I will show you in MATLAB. But you will assume that they're all powerful enough, and therefore they contribute valid spatial structure. Okay, so vectors U has a number of vectors u, several u1, u2, and etc. They are needed to describe the data. Okay, and they contain the directions, right? The directions that u1, u2, and etc. are pointing up to, in this case, 1, 2, 3, 4. Let's say up to 4, right? They are significant to representing the data. Okay, and the rest are not. You just simply put a threshold.
Yes, now I understand. So sigma is just S
Yes,
was just
yeah,
responsible for scale.
yes, and you can, of course, if we will now arrive to some expression where you can, of course, scale the contribution of these sums of squares, right, corresponding to u1, to u2, and etc., with the corresponding singular value. It is also possible, and I'm sure there is such a method, okay, for this. But it's in music approach, we don't use it, okay? Because we are matching the subspaces, we are matching the directions, okay, the shapes, if you will, but generalized, okay, shapes, and not the actual magnitudes, okay? But we take care of the fact that we are not tuning ourselves to noise by this kind of threshold. And I will show you today, we will go in MATLAB and I will show you the details, okay?
Okay, thank you.
All right, yeah. So now, yes, so we arrived at this, yes. So now let's let's again try and look at again this. So again, for each ug ux, right? We had ux here, right? So ux and sx, we wanted to maximize this. We dropped for the reasons I just described. See, thanks to you that we have something up. Yeah, we dropped c above sx, and we basically have ug transpose ux, ux squared, and we want this to be maximized, right? Now, here's a trick. Technically, we can already use this, right? We can use this and we can maximize this, but it's not really very insightful. But if you consider the continuum as we moved from single dipole, single time slice, several topographies, or single topography, several topographies and single time slice, and now several topographies and several time slices, right? Then, and these time slices are captured in UX, condensed in UX, right? Because if your data are only rank 1, if all channels are similar in shape, then you need only one UX, only one column in UX, okay? If they have two something unique, then you need two, and etc., right? So it depends on the complexity of your data, right? So, but then there is this script, there is this trick called, remember, we also wanted to find the dipole orientation, right? Things like that. So for this, we need a little bit more mathematics, very little, just a little bit. Okay, now assume that you take this matrix ug transpose ux, this is a matrix, right? And you do svd of this. Svd is the main tool, okay? So just use it anytime, okay? And you do svd of this, right? And you say you get, let's say, y sigma z transpose, okay? Where y is a matrix, sigma is a matrix, z is a matrix, and y is a matrix of left singular vectors, z is a matrix of right singular vectors, which columns are right singular vectors, and sigma are the singular values, okay? Now, assume, see what happens. Okay, I'm postulating that because this is a matrix, and this is a matrix, you can, this is a matrix and this is a 3D decomposition, so you can decompose any matrix, which is now, in this case, it's a product of these two matrices, right? But it doesn't matter. You can decompose into this SVD. Now, multiplied by y transpose on the left, and by z on the right, okay? Y transpose, U transpose G, G, right? G multiplied by UX, Z, right? Vector, my matrix is equal to sigma. Agreed? From here to here, right? Just simply multiply this by Z, because Z is orthogonal matrix. Z transpose times Z will be identity, right? And the same thing happens to Y. If you multiply from the left, this guy, Y transpose Y is equal identity, and this will be Y transpose U transpose here, right? Now see, now this is very interesting actually. I think, at least to me, it's very interesting, and I find it very, very self-explanatory in a sense. But you need some insight. Look what happens. You have matrix UG, and on the columns of this matrix, because it's Y transpose, right? On the columns of this matrix, there is a matrix Y transpose that acts on these columns, right? Because it's put on the side, but when you multiply, you take first row of Y and you combine the first row of Y, right? And you combine the rows of UG, right, with different coefficients. And Y is orthogonal matrix. It means that it's a rotation matrix. Okay. So basically, what happens? Look, this is UG. Okay. This is UX. Okay. You are rotating it, both of them, basically, in such a way that after rotation, you get a diagonal matrix. It means that you are finding in this space such a configuration that none of these rotated guys project on each other, right? But this configuration maximizes the possible overlap between each of these basis vectors. Okay. And then these diagonal elements will tell you basically the amount to which you were able to tune to adjust one subspace to another subspace. Okay. So in a very simple case, if you assume that here it's a single vector, okay, so just your data, okay, remember x0 t0, right? Then you will remember you were rotating this guy, you were taking and UG, we had very similar it corresponds, for instance, to two different orientations of your dipole, right? You're simply looking for such orientation which best fits your data, right? Orientation of dipole which best fits your data, right? Here things a little bit more complicated because we have matrices here, matrices there, but conceptually everything exactly the same. You're again looking for you are in this space through the columns, through the rows of Y. You are taking linear combinations of UG such that they match the best linear combination of columns of UX. Okay. So columns of UG, but it's rows, but I mean it's rows of UG transpose, which are columns of UG, right? Get combined. You're finding the best vector. Remember, I was drawing you this kind of thing. This, right? So you have a right. So you have a subspace, and you were looking for a vector in this space and for a vector in this space that is in common between the two subspaces, right? And it's simple, right? This is this one, right? The same thing, but we are in abstract spaces here, right? So you are finding the best vector from these guys, from UG, linear combination in this subspace. You are taking the best linear combination of columns of UX in this subspace, the best, and measuring the angle between them because they are all normalized. And the first entry of sigma here will basically be the cosine between these two best vectors. Okay, then you forget about this. You found it. You basically project your data away from this direction, orthogonal direction. You remove it, and you repeat the whole story with the remaining space. Okay, with the remaining degrees of freedom. Okay, and then you find another one. But already in this example, this other one will be this pair of vectors, right? Because they're the closest. The cosine between them is the smallest. Because if you take the vectors which are not perpendicular to this line, folding line, right, then the angle will be bigger, right? As the smallest angle is when you take the first vector is perpendicular to this folding line, and the other one is also perpendicular, but in the other subspace, right, in the second subspace. So, and this will be your second vector. It will be cosine of this will be the second entry. Of course, if you have your model, it has 3 dimensions, you will have 3 such things, right? But no more than the smallest number of dimensions in either UG or UX. Okay. And these guys are called subspace correlations. Okay. This vector, it's called, we denoted subcore of huge subspace spanned by the columns of UG and subspace spanned by the columns of UX is a vector sigma 1, sigma 2, sigma n, where n is minimum of n columns of U, G, and UX. Okay, of course, it's not exactly this. It depends. You assuming that UG's all columns of UG, of course, are orthogonal, right? And UX as well. So, okay. So again, look, from a single dimension, from cosine, in the 2 lectures before, right? We first came to the fact that we were measuring this angle, single angle here, right? Because that was your data, and that was your GX and let's say GY components, for instance, right? Right? And this guy belongs to this plane spanned by GX and GY, right? So this is GX, this is GY, right? And this is a projection of this guy. We were measuring this angle, called it gamma, right? And we were measuring the cosine of gamma, and cosine of gamma was telling us the extent to which this guy belongs to the space. And cosine of gamma is subspace correlation between this one-dimensional subspace and this two-dimensional subspace. Okay, the plane in which these two vectors lie, right? In what we are now, we are basically having one model subspace and one data subspace, column subspace, column space of U, right? Coming from the data, and we are matching the two. How we match? We can't change this, right? I mean, we can't change this, but we can tweak it, right? We can rotate it in order to compute something, right? But we can also check this for different locations, for different R, and we can see how we can fit them, right? How we can fit one to another, and finding this best fit, and then quantifying it as simply as sum of sigma sub I squared, for instance, right? And this will be our subspace correlation matrix, which we want to maximize when we are fitting, looking for dipole. Okay, what good about it? Well, the good thing about it is that we are not restricting ourselves to any time slice. Nothing. We take the data, we say that there is so much of spatial diversity in my data. How much? Well, how much is explained by UX, SX, VX transpose. It depends on this SX, on how many non-zero or like, okay, significantly non-zero eigenvectors, single vectors you have. If you have many of them, then you need to take many UXs to describe the spatial structure. Okay, UX is the size number of sensors. Okay, and they are orthogonal. They are represented, like for instance, if you had in your data, if you had two dipoles, one dipole is this, and the other dipole is this, for instance. Oops, sorry, this, right? And this is of the first dipole, this is of the second dipole. They don't overlap, right? So they are orthogonal, right? And clearly they will contribute to at least two independent columns of UX. Columns of UX will not coincide with topographies corresponding to these two dipoles, right? To this dipole and to this dipole, right? But they will span the same space as the topographies of this. We discussed it last time. So basically span of U1 and U2, in this case, for instance, will be equal to the span of G1 and G2, okay? But they will not be equal. But for this, you have a model. Now you will be looking for such for such G that fits the space well. If you found it, you found the source. Then you forget about it, project everything away, for instance, and look for another G because you have two columns, right? You have two non-zero singular values, and you need to find two sources. So and then you have another G which also fits the subspace, and then you say, hey, that's another source. And then when you take your data and project them away from the space spanned by the two model vectors that you found, you will get the remainder, you will get zero, you will not have any structure. That's it. You explain your data. Okay. So we will now do example experiment in MATLAB, okay, with this. And I will again explain all this. So there is only problem, but it will be very difficult technically to switch between the beautiful Samsung Galaxy and my laptop. Okay, but let's see. So if you have questions, you can ask now, but we can also. But anyway, we will continue and you will ask. Okay, I will try to show something on. All right. Let me. Sorry. Let me. Oh, I was very good that I remembered my battery is dying. So let me just a second. Yeah. Okay. Good. Okay. So now let me share the screen with you. Share screen. Share screen. Share. All right. Let me close this and let's come here. Okay. So again, you don't have to understand everything in this code, but some parts, yes. Okay. So let me see. Let's just for as a warm-up, okay? As a warm-up for you. Let's again see. Again, I loaded the forward model. I have everything. Okay, I pre-computed everything. I whatever. Good. We have orthogonal sources for now, right? Remember, right? These orthogonal sources, orthogonal to the cortex, right? And this is what we this is our time. We generated our time series, right? This is our time series of the dipole. This is time in seconds, okay? And we simulated our data by this line here, okay? By this line, this, okay? So we've taken the source with index II, whatever it is, I don't know what it is. What is II? Whatever, 10,006, and we simply took the topography of this source and multiplied it by the activity of the source, okay? And we obtained the data, okay? And then we added some noise to the data, okay? And here is the data, here is the source, and here is the data, okay? Each line is a channel, each color is a channel. Rank 1 data plus some noise. Rank 1 because they intersect at one point. Every channel shape is exactly the same as every other channel shape except for noise, right? Well, and minus sign, because it's essentially multiples of this shape. Multiples are the elements of vector G, okay?
I'm sorry.
Yes.
I have a quick question.
Yeah.
In time, in the first graph, what is on y-axis?
Time. It's all the same. This is time. This is time.
And
This is time in space. This is time, and this is how the source is active. This is how many nanoampere meters are there. Okay, how it's changing with time. First it's 0, then it's 0.6, then
so
it's
it's
minus.
just general. I thought the source. It's sensors.
It's a time series. It's in the source space. It's just a time series of the dipole. So I have a dipole. I have a
current.
Sorry.
Like the current.
Yeah, this is current. This is current dipole.
Okay.
If you assume that dipole has fixed length, then this is just current. Okay, first current flows in the positive direction, then it reaches its maximum, then it changes, goes to negative to 0, and then goes to negative, and then dies off. So it's like boom, boom.
Okay, thank you.
Okay, and then you take this source And because you know where it is located, it is, let me show you, what it was, a graph here somewhere. Oh yeah, display topography here. Let me do this. Display topography of G. Okay. And then you take this G, okay, which has this topography, which corresponds to a dipole that's somewhere there, okay? Like this. And then you take this topography and you multiply by this time slice, okay? G times S, right? And then that's it, right? And then you get your data. For each time slice, you get multiples of this guy plus some noise, okay? Because it's just G, the same G, but multiplied by different values. Small, zero, something big, something small, something negative, but essentially the shape is the same, okay? So, and that's your data, and then you go and search for the, we did it already, you scan, remember this, right? You take each model vector, you compute the cosine between X and your model vector, right? For I's location in the cortex. So you scan through the cortex, and then you say that, okay, let me plot the scan, and that's how the scan looked. Remember, it's not very beautiful, but this is however it is. If you don't threshold it, let's point 0.1 for instance, you will get this, okay, and the color bar tells you the cosine between the topography of the vector of the model of this with each location, right, of a dipole of yeah, orthogonally oriented, and the data. I selected the 20th slice data. Okay, so, and it shows that in some locations the cosine is pretty high, but we didn't like this picture and we went into the two-dimensional case, right? So we relaxed the orientation constraint, and then we were measuring basically the let me do this. This one is better. This one is even better. Okay. This one. We looked at this, right? Remember? And for some reason this one is not normalized. Yeah, this one is normalized. Okay, let's do this one. Okay. And we basically computed the subspace correlation. Again, I don't want to normalize it again. Let's put 9.1. We scanned and we found that that's a distribution of my metric, and of course it's not beautiful in the sense that it's still pretty large, right? But at least it's smooth, right? If I make mistake, I'm likely to be close to the point where the actual source is, and not like several gyri away, right, from it as in the first scan, right? Because we relaxed orientation constraint and we kind of alleviated some sharpness of this model, right? Because it may be inaccurate and the sharpness may do a bit trick to us, right? So therefore, yeah, and then this at maximum indeed correspond to the true source location, because if you threshold the map at, let's say, 0.9, you get something like this, right? And then if you threshold at 0.99, you get, something very close. The maximum corresponds to the location of the true source. Okay, so that was the simple thing, and this was a single source, right? And we found it, and no problem. It's really no brainer just to solve this problem. But now we say that things are a little bit more complicated, and we want to, let me just show you this. Where is the rap music? This should be rap music somewhere. I pick one at a time. I don't know if we should go over it. Let me show you just a second. Yeah, maybe let's go over it. Yeah, let's go. We have time, so let's go over it. Okay. So now, basically what we did here, we computed computed the projection of xn onto the three or two, doesn't matter, two singular vectors of our forward model, which comes from three orientations of the dipoles, right, in each location. So we had G3 in this case. For each location, for each point in the brain, it has three columns, right? And then we computed the scan, and did what I just showed you. Okay, this is essentially equivalent to computing the subspace correlation between vector G and between vector G at each location, right? And the data vector. The data vector, again, a single time slice, chosen based on the peak, right? Because I know that there is for instance, I know that there is a dipole, I see it's a single dipole, and I'm just fitting it this way, okay? And then look at the following thing. Once you have you found the maximum, right? You can scan, you can find the maximum here. For instance, let's do it this way. Let's scan. It takes some time because subcore is slower, of course, than the function itself is slower than the special case that we implemented here. But I call it, you'll see why, just to make.
Sorry,
Yeah.
I'm a bit lost. Are we doing the task when we should fit one dipole, or
No, it's still one dipole. It's still one dipole, but here I did what I explained in the lecture, which is subspace correlation. But I'm just trying to teach you the idea that this is the same as subspace correlation, okay? Because if you look at G, size of G is number of sensors by 3, okay? And size of XN20 is clearly number of sensors by 1, right? Sorry, XN20 is 102 by 1, right? And you are basically trying to find such G that matches that your X projects onto this G well, okay? So that's all. And here I did it from guts, okay? So I've taken the G, the triplet of G, then I've done SVD of it. Now, if you can look, let's say you can, for example, I equal to 1, for instance, okay? And then let's say range equal 1 to 3, okay? Then let's take, okay? Then if you look at S, hold on, S, this is not very informative. This one is informative. Only first 3, okay? These are the singular values. You can see the 2 of them are non-zero. Well, don't pay attention to this one, but because it's a scale issue. And this one is 0 because it's MEG and this radial orientation. Remember I explained last time. So that there is it's not a full rank system anyway, because your radial oriented dipole will project into 0. Okay. So there is such linear combination of dipoles which will give 0 result, and therefore this is reflected in SVD. Okay. But anyway, those are 2 vectors, 2, and so you need to fit your data X into a linear combination of these 2 vectors. So you need to find such linear combination that matches X well, okay? And this is what SVD does, and this is what this is what we measured basically here, because what we did, this is unit norm, right? This is orthogonal, because this is, I mean, they're large, I mean, but this is essentially, you can see that this is the matrix. Just images C, so you're basically interested in only the first 2. This is color coded, okay? This is the first column. This is the second column, okay? They are orthogonal. You can see that if you multiply it, U12 transpose multiplied by U12, you get identity matrix. Well, clearly, because it's the column, and then you are basically measuring the coordinate of your data in this coordinate system, okay? You're just projecting your data onto onto this 3 or 2, it doesn't matter, right? Because the third one is 0. But anyway, so, and then I'm normalizing it just to be able to see this cosines, normalized, like 0.1, 0.9, 1, not something 10 to the power of -5, okay? But it's technically not necessary. I'm just for simplicity, for clarity, okay? And therefore, this is my subspace correlation because this norm, again, it corresponds to the sum of coordinates in this coordinate system, and if it fits well, then the norm is largest. Okay, so that's it. Okay, so, and I'm doing here exactly the same thing, absolutely exactly the same thing, but using subspace correlation function. Okay, so again, at the entrance I have G, okay, and I have my XN, my data. Okay, and here again, my G, my model, and the data. Okay, and then and then I'm making subscore, and I'm just saving them in this scan. Okay, Q-scale is just a set of numbers. Okay, just 15,000 locations in the brain. Okay, so you can even plot them. You can plot QSC, and it will look something like this. Okay, because this is just indices. These are just indices, and this is the amount of correlation. And you can, of course, you can depict it, of course. You can depict it this way. You can depict it on the cortex. Here, you don't threshold it. You can depict it on the cortex like this. Here, that's exactly the same thing, right? So it's each point here. I forgot how to show the grid, but you can show the grid on the cortex here. But for each point, basically, this the fence that you just show, right? A lot of this is it corresponds to each location. It's just here the locations are organized in space, and they're just linear. The first, the second one, the whatever, and it's until 15,000. Okay, all right, 1,500. I mean, or 15,000, whatever, doesn't matter. So anyway, and this is subspace correlation. And see what subspace now you are finding the maximum, the index. You're finding the index of this peak. Okay, so finding maximum of Q scale of this music scan. Okay, you find it. And you find that the value of this maximum is 0.9917, which corresponds to a cosine of a very small angle, right? And index of this guy is 10,006. And remember, I was also 10,006 because we simulated the source and we found it. Well, obviously, because this is simulation. Okay, and in practice, like even if you do simulations like in real life, in studying the performance of your method, you usually find the maximum here, and you look at the true location, and you find coordinates of the source and the coordinates of the maximum, and you subtract the two, and you find the distance, and that's a measure of how well you localize the dipole. Okay, so now look, let's do SVD. Let's take the model corresponding to this source, to source with index 10,006. Okay, so we just took this corresponding triplet of columns of G. Okay, G3 is a matrix of size number of sensors by 3 times number of sources. And now we need just to take the proper triplet, which corresponds to index int, this 10,006, and it means that those will be columns 30,016, 30,017, 30,018. Okay, so I take these columns. And now my matrix G is my forward model for this location. Okay, 202 by 3. And then I'm doing a video of this, or a subspace correlation. But a little bit more elaborate subspace correlation because I have two other guys here, A and B. Okay. Well, B is not very informative. It's just a number. But A is so-called translator. A, the columns of A are the coefficients with which we take linear combinations of G, okay, to match it our vector X. See, let's take the first column, the first column of A, and just normalize it, okay? Anyway, it must be normalized, but I just normalize it. Hold on, norm. I'm just curious. Norm, because I'm not sure. Maybe they have factored in. No, they didn't. Okay, so let's normalize it. All right? And then see, these are coefficients that I can combine the triplet of topographies to turn them into a single topography of the dipole that has proper orientation. The orientation that was found to be the best orientation that produces a topography that fits my data X. Okay? Because the only thing I've given to SVD to subcore is a triplet of topographies, basically, right? And I said, okay, listen, here's a triplet of topographies, and combine them linearly, such that this thought vector is fitted the best way possible. Okay, so and combination of these guys means finding orientations of the dipole based on the okay. So and this way you can find I, These are just these are cosines of the angles the dipole makes with the coordinate axis. This is just orientation of the vector. Okay, and then you combine and you get a single. You multiply g, which is size. Hold on. Size g3, right? You multiply with a. Okay, you get 102 by 1 vector, which is the topography of your oriented source with the proper orientation, which matches the data well. Because if you could compute, for instance, you can make this experiment. You can say that, okay, let's compute. I'll compute core, but this is essentially the same. No, not to normalize. Okay, let's compute the angle between the first topography. Okay, between the corresponding to the x-oriented dipole. With my data. With my data. Sorry. With my data. It will be this. Okay. It's not very small. I mean, negative doesn't matter. Just different, direction. It doesn't matter. I mean, opposite direction. So it's different matters, but opposite doesn't. So okay, but still not exactly. Let's look how the first one is. The second one, 0.4. Well, not really. And the third one, well, also crap. Okay, but let's look for the optimal orientation. Here is the optimal orientation. It's A. Well, I found it from look. It's 0.9917. Yeah, this is good. All right. So you can of course do it numerically. You can take the whole space of different orientations and measure it for every orientation, but nobody does it this way. Okay, SVD does this for you. Okay, and subcore does this for you. Okay, so and then you found this proper orientation, and then you say, and this is a cosine again. And well, this is again xn normalized xn and normalized topography, and alpha will be 0.9917, of course. And then you can estimate the time series. I will, when I connect my pad, I will explain why this way, but that will be your time series, and then you can draw this whole thing, and you can, the only thing that S hat is now not as, because S was taken by SVD, okay? So, but anyway, this is a time series, and you remember how the time series looked. That's the time series of our dipole, okay? So we basically solved the whole problem. We found the dipole, and we found its time series, okay? Now,
we just asked the program to find the time series.
No. We use this expression here. We use this expression to find the time series, but this is essentially we just took the data and projected the data on the topography of our source. Which is G times the data gave us the time series, but the topography has to be normalized so that it's you get the time series. See, look, let me try to write it here, okay? So your data is G times S, okay? Well, plus some noise, okay? You found this G, okay? You didn't know it before, but you found it, okay? So now you know this G, okay? Now you say, now I'm interested in S. I need S. And I tell you, well, multiply this data on the left by G transpose. G is a vector. Okay, let's make it G like this. Okay, so it's a vector. It's a column vector. Okay, if you multiply it by G transpose, this one is transpose. Okay, you multiply by G transpose, right? And this one by G transpose, right? And then you get this, right? And then if you want S, you may want to do this: J transpose divided by G transpose multiplied G multiplied by X. Okay, so see this one, and plus whatever, plus noise. But what can you do with noise? It's noise. I mean, you ignore it. I mean, so of course you will get it. You will get something left in the noise, but some noisy, time course, but the main shape will be there. So anyway, so this is a vector. This is a scalar, just the squared norm of this vector. This is G transpose G. It's a squared norm. and you multiply it by your data. And because from this expression, it follows from this expression. Because see, this guy also a time series, but this time series is G prime, G transpose G is stronger, more amplitude than the real S is. Ignore the noise. So you need to divide it by G transpose G, okay? So, and then you get your S. So that's essentially what I've done here, okay? So this one, is this one, and this one is this one. Normalization, okay? So that's it, So I found, and we found the time series. And if we go back and generate S again, just to, yeah, let me generate S again. S0. Okay, S0. I remember I saved it as S0. Okay, let me go here S0. Yeah, close all. Yeah, F9. Okay, so see. Well, I normalize them to avoid there's some normalization issue, but I forgot, ignore it for now. Because it depends on the amount of noise and blah blah blah. But anyway, so here the blue one is a true one and the red one is the recovered one. Okay, so you found this location and you found the time series. Very nice. But that was very simple because it was only one source. Okay, it was basically no brainer. It was nothing to do. Okay, now let's simulate the two sources. Okay, we simulate the two sources. We take two topographies, again orthogonal, again fixed orientation, whatever. So yeah, but anyway, when we simulate, we can use fixed orientation. I mean, how? Because the dipole is something which has, we don't know it, but it's fixed. Okay, so and then simulate your data and simulate your noise data. Okay, and then plot all this. Okay, plot all this. All right, now these are the time series of the two dipoles. The first one and this is the current. Okay, this source comes first, then it's positive, but this one is negatively active, but then this becomes positively active, this is negatively active, whatever. And this is your data. Okay, see, but that here is already very interesting story, because you see two clear peaks in your data, but none of these peaks technically correspond to the case where only one dipole is active. There are two dipoles active. Here active because this one is negative, this one is positive, and at this peak also this guy is active and this guy is not silent. I mean, so basically in order to feed the dipole, you need to choose. Let's assume magically that Father Frost came to us and told us what are the time series. Okay, and then we said, okay, then to find the source, I need to feed this source to this time location. Okay, because this is where this guy is active and the blue one is silent, right? So this one is approximately if you take, these are synchronous, but here's the samples and here's the time. The same thing, just the number, it's a number multiplied by delta t. Okay, here now number by delta t, and this is just now. Okay, so you basically take this, maybe 50, maybe 60, whatever. And for the first source, it may be 20 or maybe something here, right? And let me try to take these peaks and feed my data. Okay, so here's the topographies of these two sources, of the sources of the data at these two locations, and you indeed can see that they correspond to two different dipoles, right? One is shifted, the one is here, and the other one is here. Okay, so one is here, the other one is here somewhere. Okay, and then you try. Let's do the scrolling. Let's do the scanning. Okay, so it's x25 here. Let's do again the scan. Feed peak 1, and the second peak and feed peak 2. Okay, so let's feed both peaks. So with subcore, just the way, very trivial, everything exactly the same. But again, we do not assume fixed orientation, right? Because again, we are doing subcore with model G, which has 3 columns per. The orientation of the dipole is fixed, but we don't know it, and therefore we are looking for it. Okay. Okay, it's done. Okay, let's plot scan Q1. Okay, it's almost there. Okay, and then show ground truth. sorry, I'm not using this plot, but anyway, let me show you the ground truth. Okay, and so yeah, there are two of them here. Okay, so yeah, so this is when you've manually chosen pick one and manually chosen pick two, then thresholded, and yes, you kind of, yes, yeah, you found it. Okay, great. But you use the extra knowledge, okay, which you don't have actually, right? And you can't do it like to every dipole you want to fit. You will be looking for this is impossible, okay? And again, see, you found, but it's not great. It's still shifted, and so it's kind of iffy. All right, so now. And then you say that now things will be even worse if you were to simulate the data that overlap stronger, okay? Now see, this since I generated the data, but now the time series overlap more. So they're not like shifted one with respect to another, but they're closer. Now it's even more difficult to find good peaks to fit the data, right? Especially if there is noise, no, they're basically hopeless. Okay, so therefore we are not even considering it here. And you can look at this topographies again. And let's now do music, the one that magic. Okay, first of all, let me show you the result of it so that you're impressed. And then and then and then we will. So this is a music scan. I will show you all the steps, of course, but just to show you the result. All right. Look, these are the singular vectors of the data, single values. You see them, two of them significantly non-zero ones, and the rest are small ones. So you know that your data are rank 2 approximately, like numerically. And then let's show look at this. No peaks chosen, nothing. Two locations of your sources are found quite beautifully with no effort. Okay. So let me explain you how it's all done. Basically, I explained it already to you, but show you here. All right. So you take your data, which is xn. Let's close everything and plot xn prime. All right. This is your data. Okay. You can also, if you are more comfortable with viewing it as xn this way, you may look at it this way. Okay. It's your data. They're color coded. Okay. Each row is a channel. The intensity of the code or of the channel is coded with color. The warm one is a positive. The cold one is negative. Okay. So all right. Now you take your data and you do SVD of your data. Okay. Yeah. You take SVD of your data. And now see what you do. You are saying that, okay, I have S, let's say 1, 3, 1, 3, because, so I see this one is large, well, compared to the other one, of course. This one is large. This one is, well, I mean, twice, half as large, right? And this one is almost 8 times weaker than this one, okay? So, and if you plot stem diag, stem is just, just this kind of plot. Yeah. You got this guy, 1.7, right? 10 minus 5, 0.9, approximately 0.8. And then the rest. I mean, I've just shown the third one here, but they will be all small. Okay. So you and then you say, okay, my data can be approximated by only 2 components. Let's check this. Let's say that your X noisy approximate is U first multiplied by S11 multiplied by V first transpose plus exactly the same construction, but for the second one, 2, 2, 2, 2. Okay. Then close all. See, plot xn xn. Let's say, let's plot it with red, with blue. Okay. No mistake. This. Okay. Hold on and plot xna with red. Okay. All right. So see the time series, the blue ones and the red ones overlap very well. Okay. So the red one is approximated, and the blue one is original. We got rid of some noise, see, right? Because the red ones are smoother, right? And they very well represent the data. How well they represent the data? You can plot this thing. Green. Okay, that's your error. That's the blue one for each channel, of course, right? I made them with the same color because if I use them with different colors for different types of data, it will be difficult. But each time series case still is just a vector. Yeah. See, it's a line, but it's so this is a difference. So my matrix, my only two components represented my data almost completely. Okay, so you can do it this way again. You can represent like x original, and x and a minus x and okay here. I just concatenated the three plots. This is the original data. See, this is denoised, and because we focused only on the main dimension, the most powerful directions, these are my data, and this is the difference between the two. No structure in my difference, okay? Whereas if I make my x and a only from the first component, and we'll do the same trick. Yes, we'll do the same trick. See, this is my approximation, but I still have some structure left. Not noise, but some structure. And this structure is taken care by the second component. But the rest is noise. So, which means that the columns of U1 and U2, they span the same space as the model, but they're not equal because if you were to look how much the first dipole contributes to the data and how much the second dipole contributes to the data, they're pretty much equal. You know, they will not look like this. They will not be preference to the first one or to the second one. But this single value decomposition works in such a way that the first component captures maximum amount of information about the data, maximum energy. The second one does maximum in the projected space. And the third one does another maximum in yet another one, another time projected space, and etc. All right. So
I'm sorry, can I ask
yes.
this
Yeah.
one? Where does the substructure come from?
Sorry.
Where does the substructure come from? The one on the right you were showing.
It's a difference between the approximated data and the original data.
Okay.
Because it's there. It is there. I mean, you know, because you just used only one component here. See, because x and a here, x and a was equal to this. It didn't include the second component. And the second was informative. You can see even more contrast if you do it this way, and then you do it this way. See, this is how much the second component explains.
Okay.
And that's how much is left. And the further you move with components, the smaller the difference will be, okay?
Okay.
The first component explains most. The second component explains second most. The third component explains third most, and etc. Okay, but if there is a difference, there is a big drop between how much the first and second component expresses and how much the third one expresses, then you have the right to say that, well, listen, my data have only two main components. That's what I answered when you were answering the question about where you came from, why we dropped SX. That's exactly here. We drop in SX because it's insignificant. Everything after the second component is insignificant. Okay, so and this space spanned by the first two columns of U is called column subspace, signal subspace of your data X. Okay, and then what you do the same thing. You just do the scan. You just do subspace correlation between the model for every location in the brain and your signal subspace. Okay, I limited to the first two because model, because no, the model I didn't limit. No, that's okay. So yeah, I've taken on the first two singular vectors because they have the data. The rest is not about the data. The rest is about noise. Okay, and I found the best linear combination that in this space and in this space, so that the angle between them is minimized, the cosine is maximized, and that's it. I did the scan, and I plotted the scan. Okay, and there it is. See, the beauty here is that I didn't at all have to select any time slice, any. I just taken the whole data, and I asked to check for the spatial structure what is present in my data, and I tried to match my model against the spatial structures that is present in the data. Okay, and I found that my model hits the spot here and here, and not everywhere else. There is a spoon of tart. Okay, let me show you a spoon of tart. If you do not threshold the scan, the scan looks like this. It is not horrible, but it's not great because it's too smooth. And if you have a single source, it's not a big problem. You know, just find the maximum. You can always find the maximum. But if it's two sources, you know, one is here and the other one is here, right? It's a little bit more complicated how you find it. I mean, what? I mean, you know, you find the first one, and then what? You will find these bumps, little bumps, but this is already artificial intelligence problem, and we would like to avoid it, right? Because you want to do it automatically, right? So John Compton Mosher, PhD, came up with this idea. He was a student of my professor Richard Lee here at USC, and he is terribly proud of this idea of his. Okay, what he did is actually this is pretty cool idea. The only thing is that I mean it shapes your thinking about this, which is good, you know. So what he said, okay, why don't you plot this kind of map? This is called subspace scan. Subspace scan is simply, you know, the amount of subspace correlation, you know, in this. Okay, you plot this, and then you, by the way, yeah, and we've taken here the first subspace correlation, the first angle, the best angle, okay, the smallest angle, okay, to be to Q1, because technically Q has two elements to it, right? So, but anyway, you take this, and you find the maximum. Just maximum. It's very easy. No artificial intelligence, just maximum. Okay. So you do this. Let's do this. Let's find the maximum. Okay, of this scan.
But do I get it right that this maximum will not be the same as the maximum as the value of the first dipole?
No, it will be. We hope it should be.
It will be.
It will be. We hope. Yes.
But it has contribution of the information that we originally explained with the second dipole. Why
yes. Because a very good question. I don't know at which level you're asking it, but the question is good. Okay, so see, because the space is big, because the space in which you are finding this guy is big, and the subspace of 2 dimensions, and chances that this 2-dimensional thing will be matched by something from your model when the subspace is large, are not very high, and therefore but still, if you look at it, the maxima, the map is pretty smooth. So it's pretty large set of locations that fit more or less okay into your data, right? It's not like, and this is a drawback of the method, of the whole music approach, of the whole multiple signal classification approach. The drawback is that the scans are very smooth. Okay, and therefore, basically, if you see subspace correlations values below 0.97, you usually say no. This is like this is whatever, because it would correspond to well, if let me put a color bar here, okay? Okay, 0.7 is already 0.9, even 0.9 is this, okay? Is this It's pretty far away from your source, okay?
Yes.
So you are interested
Okay.
in these kind of values, okay? So very, very close to the hotspot. And this is a drawback of the method, yes, because this fine structure is dictated by the accuracy of the forward model. If the forward model is not accurate, then the maximum will be shifted. But I actually played with it here. So see, there is a here. No, hold on. Where I was doing the scan, I was adding the noise somewhere to the model just to check. It's kind of stable, but not super stable. Okay, but anyway, but yeah, it's a problem. Yes, it is a problem, and it's actually this problem is something that needs for the one to be aware of when you're doing simulations, because you can do so-called inverse crime. You can simulate your data with the model that you know exactly. And then you can say, oh, I've developed this beautiful method based on this exactly known forward model, and how it's see how greatly it solves and outperforms everything possible. Okay. But you never ever have the model which is exactly the same as the model the data came from. I mean, just no way. Okay. And therefore, you always do, when you do simulations, you use some model to simulate the data, and then you corrupt this model a little bit, to some extent, so it remains publishable. Okay. But anyway, if you corrupt it completely, you won't publish anything. So, and pretty much that accuracy about 10%. Okay. John Compton Marshall, PhD, had a paper where he evaluated typical accuracy of all the forward models. Okay. And it's if you talk about spherical models, it's on about on the order of 10%. Okay. So
accuracy
it's
is 90%.
90%. Accuracy is 90%. The error is about 10%. Yeah. So it's pretty accurate. But there is one trick here, is that the accuracy is not everything. The main thing is how the model is corrupted. If the model is corrupted by the white noise, I mean, all corrupt like independently, it's not very dangerous. It's not a big deal. But if it's corrupted with some structurally smooth corruption, then this is the problem, and that's usually the case. So therefore, when you are simulating, you need to do the corruption, but not just by adding the proper amount of noise, to your model, but to somehow simulate the smoothness of this noise, as well. So anyway, so let's find the maximum first. We found the maximum, and the location of this maximum, likely 10,000, 10,600. Well, this is good. This is the first source. And then you say, okay, we take the topography of the matrix corresponding to the first source, do again subspace correlation, Q is 0.9987, and then we say, okay, our orientation vector is A, okay, so our orientation vector is A, we find the oriented topography, okay, and save it. That's it. This is our first topography. Now, we do projection away from the topography that we just found, away from this first source. Okay? And remember, the first scan looked, we had two clear maxima, right? I mean, well, not very clear, but if you threshold, you see them very clearly, two of them, right? Now you project your data and your model away from the found dipole, from the topography of the found dipole. You remove its contribution from the data, basically. It's just a smart way of saying, you project it basically, okay? So, and then you do this, and then you do another scan, okay? It's _2, meaning that it's a second scan, okay? And let me just wait. Yeah, and then you plot it. Let me close everything, because otherwise it will. My graphic card in this computer is not compatible with MATLAB very well. Okay, that's the scan. Only the second one is, if you want to see how it's without the thresholding, let's see how it is without the thresholding. Here, okay. So it's gone completely, almost completely from this first source, because we removed it from the data. We removed, and we now the remaining, and again, here you look for the maximum. So you don't have to look for local maxima, which is always very difficult, especially in 3 dimensions or in 2 dimensions, in this on this surface, right? But you look only for the maximum maximorum, okay? And that's it. And then you again find the maximum. You're again finding the maximum of the second guy, okay? You found the maximum, you found the subspace correlation, you found the orientations, and then find again oriented topography, and the best vector in the single space, but we don't need it. Okay, and then you add to your forward model matrix. Now, see, matrix GG now, GG is 102 by 2. It has 2 topographies of 2 sources that you have found. Okay, and this matrix, you expect that this matrix is equal to where is this? To this G ort II and G ort JJ columns. Okay. So you expect you expecting it. So you can if I didn't move anywhere, you can do this II JJ, and you can co-add this with sorry, G ort IIGJ with GG. And I did goof somewhere, maybe not. Hold on. G ort II GG. This is very strange. So yeah, I know why. No. Hold on. G ort. Hold on. Let's try this. G ort II. Okay, let's try this. Core F G ort II with GG1. Yeah. So see, it's almost, I mean, it was negative, but it just corresponds to the dipole, which is oriented in the opposite direction, but it doesn't matter because at the time series will be just negative. But but the orientation, you multiply the orientation by the opposite orientation by the negative for activity, you'll get back the data. Okay, and then for the JJ, the second one will be it should be a little less, or maybe a little less, but still pretty good. Okay, and then C, again the same trick. Now you know this GG, you don't know S, you know the data. Okay, you again do GG transpose okay, GG transpose, okay, and then you take this, but this is matrix now, so you can't just divide. You have to take this and say I want inverse of this. Oh, sorry. Okay, and this gives you S hat, whatever, S hat. Okay, so this is multiplied, and this way you get your two time series at once. Okay, exactly the same trick. Before you just had one time series. Okay, one channel. Here just 2, but I mean you already have the matrix, and this is you are solving this in the least square sense. You're solving this matrix of equations. This one that was before here, right? This one, because you have X, you know G, you don't know S. Okay, it's like regression problem. Okay, this is like in ANOVA you do basically similar thing. So you don't know regressor. So what you do, you have to take the inverse of this and multiply by X, right? But the inverse of GG doesn't exist because GG is tall. It's like when you did measurements of 2 springs. Two sprints, and you put in each row is your measurement, okay, and S is your coefficient of how you say it, of plasticity, okay, and then you have many measurements, and now you need to find the regression, okay, you need to find the same story, okay, except that you also have time dimension as well, but who cares, just the same for each time slice, and then yeah, so you get it here. You get some Yes, here is your GG. Here is your, this is equivalent to pseudo inverse of GG, okay? It's what this GG transpose inverse multiplied by G transpose, it's equivalent to, it's just simply pseudo inverse of GG, okay? You do this, and then you do this, and there we go. So the edgy one are the estimated ones, and the smooth one are the true ones. Okay. So you found the sources, both sources, and you found both time series. Okay. And without any, basically without any assumption. Of course, yes, we used sort of inverse crime here. We used for exactly the same forward model, but you can play with, I mean, I can give you homework and I can ask you to break music. Okay. To break music by corrupting the model, for instance. Or by adding the noise. And it's actually pretty stable if you're given quite a bit of noise, just the data noise is pretty stable. And it's worked quite well. I used it many times and I used it for fitting spikes, epileptic intellectual spikes, and was behaving very nicely. And yeah, it's a really practical method. And now the good thing is that you have a chance to understand it, okay? Of course, you can use M&A Python and ask fit dipole fit, okay? And it gives you dipole fit, okay? And you say, okay, great, this is my dipole fit, okay? But you can't critically assess what it did, okay? With this, I hope you can now, or at least, after you go over it one more time and try to sort of digest this, because I understand this is not a very simple stuff. I can tell you that I was trying to explain it to my colleague with whom we wrote actually a pretty cool paper in a pretty cool journal. And he is a physicist by training. And I tried to explain to him rap music. I failed. I'll try to do it about 10 times. And it's not because I'm a horrible explainer. Well, I'm not the best explainer, I'm sure. But I mean, he's a physics major and I did it 10 times. And it didn't work out. Okay. So it's not simple. From this, I conclude it is not simple. Okay.
Yes.
But again, at the same time, it's not difficult in the sense that it doesn't use any advanced concepts. It's just very basic linear algebra, projection, cosines, multidimensional spaces, a little bit of abstract thinking. That's all.
Yes. I have two questions.
Okay.
One is about this graph. It surprised me the first time, and it continues to surprise me. Why do you say that it's our original time series, it's our model time series, Why do we have smooth original and model is not smooth?
Yeah. Well,
I mean, in my по логике, according to my logic, it should be the opposite, because we use some approximation.
No. Look, we simulated the data, right? We simulated S. We simulated them as exponent, as a sort of side,
yes,
and they're without noise. But we applied. See, remember that when we see here, we applied pseudo inverse of G to the noisy XN. Okay, so see, this is your X. Oh, sorry, X0. Yeah. This is your original data. Okay, they're smooth. This is your noisy data, but because you always have noisy data, so that's what you have. And we applied to this data, we applied the pseudo inverse, basically this, and this noise, of course, leaked into the estimate of the time series.
Okay.
This is normal. This is logical, I would say. Yes.
Okay. And another question is, do we have? Okay, I should say that I understand these things only locally. Maybe I'm thinking something wrong. My question is, do we have some quantity, some number which is, I mean, not goodness of fit, but some number that we except besides cosine, значение cosine, that will tell us how good
how well we did. Yes, you can. Yes, you have cosines, but that's okay. You know, cosines tells you how well your model fitted to the data.
but
Okay.
yes, but as far as I understood, cosines tell about one dipole.
Yes, you're right. Yes. Well, if you have, let's say, if you fitted 3 dipoles to the, yes, you're absolutely right. What you can do, you can say that your synthetic data is equal GG transpose times S hat. Okay. This is something you already found. This comes from your and you have your noisy data. Okay. And now you plot X synthetic X noisy first. Let's with red one. Okay, prime. Okay. Then you do hold on. You plot your synthetic data with blue. With blue. There is some again. I'm sorry, but no, actually no, that is okay. Yeah, I thought there was some problem, but was problem before with the scaling, but no, now it's okay. Yeah. And now hold on, and now this is your goodness of fit. X noisy minus X synthetic green. Sorry. Yeah. And your goodness, if you want the number, then take Frobenius norm of this guy. This is D. Sorry, again, same story. And then a norm of vector D. Okay. And well, it doesn't tell you very much because it's not normalized, by divided by the norm of xn here, and this is the error.
This is the error.
Yeah, 27% of error.
Not very good, I think.
Well, no. You can't say it's not very good because your noise is white. If I add you more noise, you will get like 0.5 error, but you will fit exactly the dipoles in the proper locations. It's just because your data are noisy. I mean, your data are noisy, but the noise is very good in the sense that it's not adding any bias, but because there are some noises which add the bias. Okay. So the literal quantity doesn't tell you, it's just the power. No, okay, hold on. You need to divide it. It's all over all time points. You need to divide it by the number of time points per time point. Okay. Here. All right. So it's not that bad. Per time point, each time slice has this much of error of reconstruction. Of course, if you sum them all up, then yes.
Can I ask
if you take quadratic error, then but it was this way, yeah. So it's but still 2%, 3%, you know.
Yes, я правильно понимаю, что это обратная единица, обратные значения, точнее, ну, в общем, обратные тому, что вы показывали на вот этой вот color bar, что вот там, где желтенькое, вот выше 0,9, вот.
Ну, в color bar я показывал эти, как их называют, subspace correlations. Да? Это, как вы правильно сказали, было про каждый диполь, в каждой точке, насколько это диполь fits.
Точно, да, все, окей.
Это уже, как вы righteously asked, it's a measure about the whole thing, how well we fitted the data. And see, the thing to look at when you talk about the number is here, right? But number is not everything. You look with your eyes, okay? And you look with your eyes and you say, is there any structure left in my error? Is there any smoothness left in my error? If there is no smoothness, that you did great, okay? It can be large, but if you explained all structure in your data and all what is left unstructured noise, that's it.
Yes, and it's good seen from this gradient, these pictures, blue pictures with lines.
Yeah. This is, yeah. And also, and by the way, this is how the brain works. Okay, if you take, like, the brain is a hierarchical system which processes information and blah blah blah. You know, there's context and at each layer you are trying to predict the data, and you are predicting the data, and you have the error, the prediction error, and you're trying to explain the data, and if this prediction error is not statistically wide, if it has structure, then error makes it up to the second layer. And in the second, more abstract layer, you're again trying to predict this difference. Again, and you are moving up to the top until you have explained the variance, until you explain the structure in your in what you measured. If you imagine, if you take the stimulus, like if it's beep, for it's a beep boom, like beam beam boom, right? The difference between beam and boom is encoded very low in the hierarchy. It's very easy to explain it, and after the first couple of layers you don't go further, and you will not see any signal propagation, nothing in the brain. But if you say that, like, I don't know, like mama, papa, mama, papa, you of course will have some basic stuff because ma, ip are different, right? But there is some more to it, higher level structure, and then you will be explaining it, and you will see activations very far away in the structure. It's all non-linear, it's all complicated, but essentially this whole thing is very similar. You are looking, or the brain is looking, the brain circuits are looking for the structure. If the structure is absent, that's it. The model that you already use the information in the data to update your model.
Yes.
And this model is something, your model about this world, okay? That's what you think about this world. That's it, yeah. So basically similar thing is here, but on a very low, linear, basic level, okay? So, yeah.
Okay, thank you.
Yeah. Okay. Yeah. So I think we are already, we're pretty much done, right? It's 14:17. Are we supposed to be done by now, right? Yeah, I think so. Yeah.
Yes.
Okay. Yeah. All right. So we will do our best, and we will do it. We will give you the homework tomorrow. Dasha will share the lecture notes, and we'll share the I will stop recording.